Det är så stor avskjutpersonal som jag tror. Jag kan inte tänka liksom, varför har man inte just till sånt här tänker man borde ha någon sån dedikerad.
Hi everyone, we just have a little bit of a challenge with the sound. Please stay put. DCOE is checking and we will start very soon. We are sorry about that. The perks of doing it live.
Ran away in terror as the fire destroyed everything without mercy. Lions, zebras, elephants, rhinos, gazelles, and many other animals sought refuge. One day, a great fire broke out in the forest. Faced with the advancing flame, all the animals ran away in terror as the fire destroyed everything without mercy. Lions, zebras, elephants, rhinos, gazelles, and many other animals sought refuge in the waters of a great river. But the fire was about to reach them too. While they were all arguing heatedly about what to do, a tiny hummingbird dived into the river and, after taking a drop of water in its beak, heedless of a great heat, dropped it over the forest invaded by smoke. Fire did not even notice and continued on its way carried by the wind. The hummingbird, however, did not lose heart and continued to dive, each time collecting a small drop of water that it dropped on the flames. This did not go unnoticed, and at one point the lion called to him and asked, "What are you doing?" The bird answered, "I'm trying to put out the fire." The lion laughed, "You think you can put out the flames?" And he and all the other animals began to tease him. But the bird answered, "I'm doing my part anyway." Good morning or afternoon. I'm Gianluca Nicchiotti, and in the next half an hour, I'll try to show you how the hummingbird story could represent a metaphor of the contribution of optical measurements for condition monitoring in the context of decarbonization. This is a summary of today's presentation. We will start discussing how the increasingly restrictive emission standards compel power generation system to operate within lean combustion limits in order to reduce the formation of NOx and CO2, and the impact it has on the lean combustion and the usage of hydrogen and other not polluting fuels. Then I will introduce you to the working principle of interferometry for sensing and its benefit. Next will be the description of a Meggitt sensor in terms of architecture and main characteristics. In the last part of this presentation, we will discuss the result of a test campaign. We made an ad hoc test campaign in order to compare the performances of optical sensors and piezoelectric sensors. We'll see the results. And we'll go to the conclusion, where I try to give you the most important elements of today's presentation, and I will present you also the current development in Meggitt. So let's start with the green push. This parameter shows how more stringent environmental requirements for gas turbine push towards the development of new methodologies to sense and monitor the combustion process. Particularly, we know that at the end user side, we need zero or almost zero carbon emission, low NOx emission, and this reflects on the customer side in the need of having lean combustions or using new fuels like hydrogen and ammonia. And finally, this flows down to the sensing technology with the requirements for flame monitoring, for prognosis and diagnosis of lean blowout and flashback. How much is important, the capability of reducing the safety margin is clearly shown in this Georgia Tech plot, where it's evident how reducing the safety margin here in this x-axis reduce greatly the emission of NOx. So we have two main ways to reduce the pollution. One way is to have a linear combustion. Again, so the push comes from emission standard and also from operational savings, because we will use less fuel. And going to lean combustion, we need to have the capability of managing lean blowout condition, that is the condition under which the flame extincts because there is too few fuel. If we are able to manage the lean blowout, we can reduce the safety margin. As shown before, we can reduce the emission of NOx. But in this case, as we will see, we will need new sensing and data processing methodologies. So the lean combustion has the following challenges. It is detecting lean blowout and the better capability of monitoring flame instabilities. This because we have a higher reactant flow velocity, and sometimes the reaction time is not able to keep the pace of the mixing time. About the hydrogen, again, the push comes from emission standard decarbonization. So we may go to partial or total hydrogen combustion, but in this case, the hydrogen combustion is more prone to produce flashback, and we need to detect or even to prognose flashback. So again, We have the requirement of having new capabilities in terms of sensing and processing the sensed data. Hydrogen combustion presents new challenge in terms of sensing and in monitoring and piloting the combustion itself. This is because we have a higher flame velocity, we have higher temperatures, and also the flame color changes from visible to ER. So the flame is completely invisible if we only burn hydrogen. So the consequences are that we have to be able to monitor flashback, to detect flame instabilities, and also to detect the flame, because as I said, it may be invisible. In terms of sensing technology, nowadays technology for controlling the flame are based on ion emissions, on the analysis of the flow speed or the flame shape, and also the analysis of the pressure and the temperature. So the main sensors are based either on chemiluminescence, or we can have also quantitative flow visualization made through particle image velocimetry. Sometimes high-speed CCD camera are used in order to detect the flame presence and its shape, but more often are the dynamic pressure sensors based on piezoelectric technology that are used in order to measure, as I said, the pressure. All this sensing technology have drawbacks, which may be related to maintainability or operating temperature, or response time in case of a CCD camera, and, as we will see more in detail, the signal-to-noise ratio at high temperature and low frequency for the dynamic pressure sensors. Emission reduction pose new technical challenges to sensing systems inside the combustor. Most of these challenges can be effectively tackled by optical sensors. And here we're talking about the temperature aspect, reliability and sensitivity aspect, but especially all the needs related to flame health monitoring can be solved by the use of optical sensing systems because they do not have the low frequency limitation that conventional sensors have. Here you have a table, and we are going to discuss all these points during the explanation of the result of our test campaign. So let's talk now about optical sensing and what it is, how it's done, and what are the principles that are behind the optical sensing system. First, I want to give you an idea about the Meggitt positioning, about the optical sensing technologies. We know that they are quite well developed and deployed in the medical environment. And about the power generation and also the aerospace, there is an ongoing transition from the research to the implementation of in-service asset, as it is the case of our optical sensor. Main providers are SMEs, providers of the technology, and Meggitt has closed some agreements with one of these technology providers in US. The idea of Meggitt is to become a world-class integrator of optical sensing technologies for both power generation and aerospace. And we have already active partnerships and projects for the fiber per rod, but also for the fiber Bragg gratings. With this slide, I start introducing you to the working principle of a Fabry-Perot sensing system. Sensing system is made basically of two parts: an interrogator, which stays in the control center, and an interferometer, which lies in the combustion chamber. In the combustion chamber, the pressure modifies what is called the interferometer gap, which modifies the light which is sent from the interrogator to the interferometer, and the modified light returned to the interrogator is then analyzed, and the result is converted in the end into the pressure value. The Fabry-Perot interferometer, which has been used, has some peculiar characteristics. So, Fabry-Perot interferometer is basically essentially a cavity where on the two sides we have
nel senso che noi abbiamo la confidenza che tutto il
one
materiale
of the mirror is attached to the diaphragm in such a way that the cavity size may change when we have more or less pressure or a change in temperature. In our case, we will use a low finesse interferometer, which means that the reflectivity of the two mirrors is low. And this plot shows how different type of finesse change the modulation of a wavelength. This is in the case of a low finesse, f equal to 2, and this is in the case of higher finesse with f finesse equal to 10. Another characteristic of our Fabry-Perot sensor is the fact that we are using a wide band light source with about 50 nanometers of full width f-half maximum, which is this size. And we will use a wavelength of about 850 nanometers. As mentioned before, the Fabry-Perot interferometer is essentially a cavity made by two reflecting parallel surfaces. Here, the reflected light is modulated in frequency as a function of a cavity size. Why this happens? This happens because at every reflection of the phase of ray increases of delta, where delta is determined also by the L, where L is the dimension of the cavity itself. So in the end, we have a reflection coefficient which varies with lambda, with a wavelength lambda, which produce a modulation of this kind that we show already. So in this case, we have a low finesse Fabry-Perot cavity. In this case, we have a high finesse Fabry-Perot cavity. And the finesse is linked to the reflective coefficient R by this simple equation. Sensing technology presents several advantages with respect to the other sensing technologies we presented before. We have an improved sensitivity and accuracy, especially at low frequencies. We are inherently insensitive to EMI perturbation, because we do not need to have electric signal inside the sensor. It's also inherently safe. We have a small size. It can be used in a multiplexing architecture, and especially, underline especially, we have multiple sensing capabilities. So we show that the light modulation happens as a function of a size of a cavity. And this means that the measure spectrum we receive in the interrogator contains essentially the information of the gap dimension, and any physical quantity modify the Fabry-Perot cavity dimension can then be related to the reflected spectrum. And so any physical quantity can be measured if we measure the size of a cavity. And this means that we can use Fabry-Perot sensing for dynamic pressure, but not only, also for static pressure, for temperature, for displacement, for vibration, etc. Now that we have seen the basic principle of vibro-meter sensing, I'm going to describe the Meggitt sensor. As we already seen, for the vibro-meter, we have essentially two parts. One part is the sensor itself, that stays in the Zardus area. And the other part is what we call the interrogator, which contains an optoelectronic module and some data processing algorithm. And then the result coming out from this system can be used to have more sophisticated monitoring algorithms that we are going to describe a little bit in the final part of this presentation. Here I'm going to describe a little bit more detail what happens. So in the combustor side, we have a vibro-meter cavity connected to a diaphragm. When the pressure comes in the combustor, this modifies the size of the diaphragm. And this determines a modulation of a light which enters in the vibro-meter cavity, a modulation in frequency. This modulated light, modulated in frequency, is sent to the interrogator, and the light passes through a wedge. What does the wedge? The wedge converts the frequency modulation into spatial modulation, and the spatial modulation is collected by SCCD and then analyzed by an FPGA or a processor. Doesn't matter. What matters are the algorithms. So what happens is that this spectral modulation is converted into this spatial modulation, which can be easily analyzed in order to extract the pressure measurement. So now you discover that inside the Meggitt system we have indeed two interferometers, not just vibro-meter interferometer, but also the Piezo wedge. What is a Piezo wedge? The Piezo wedge is made by two surfaces intersected at a very small angle theta, these two surfaces. And it transmits the light according to this relationship. Again, we have a frequency modulation. But what is important is that the light is maximally transmitted in this case at the point where the Piezo has the thickness which corresponds to the size of vibro-meter cavity. This means that on the CCD array which is behind the Piezo, detecting the peak of the light, we can determine the size of a vibro-meter cavity. So substantially, what happens is that the Piezo wedge converts the spectral modulation provided by the vibro-meter into a spatial modulation. Now we want to resume the two main math relationships from the optical point of view, of course. So we have equation which deals with the vibro-meter reflectivity, which says that the reflectivity is a function of a wavelength, is a function of the finesse and the path delay. And we have a second equation which determines the wedge transmissivity, which is again a function of a wavelength and again depends on the finesse, but this time is the finesse of a wedge. When Meggitt started thinking about optical sensing, the main goal was to improve the Piezo performances. Especially, we were focusing about the fact that Piezo do not give very good results for frequency lower than 50 Hz at high temperature. More, we want to be immune to vibration and to EMI. So these are the initial goal of designing an optical pressure sensor. And this table represents the main characteristic, resumes the main characteristic of the optical sensing system. So you have described here what is the dynamic pressure range, the frequency response, which go reliably from 2 to 20 kilohertz, the precision, the accuracy, which overperforms again the accuracy provided by the piezoelectric sensor. The operating temperature range, which goes to 600 degrees, but activities are in progress in order to change materials and to go to temperature as high as 800 degrees Celsius, and the operating pressure range is up to 30 bar. So once we've completed the design, it was the time to make this mesh, optical versus piezo, that I'm going to describe next. We knew very well that piezoelectric sensor had low frequency limitation. Low frequency, we'll see, is very important to detect the limb blowout and flashback. What we knew is that the increase of the temperature caused the drop of the sensor resistance, which in turn determine a significant increasing of a noise level, but especially mask the behavior at low frequencies. So we decided to design a test campaign in collaboration with Graz University. And in order to compare the optical system with its piezo counterpart, in several realistic scenarios representative of a gas turbine combustion, this has to be done in a controlled, precise, and repeatable manner. We want to know exactly what we were doing within the combustor. And we focus on several aspects, which are listed here, which goes from the electromagnetic interference to the perturbation due to the vibration, and to the detect of event like ignition, flashback, change in regime, and limb blowout. The test setup we had was done in such a way that we have in the combustor 2 piezo sensors and 2 optical probes, and we can also produce a plan on different conditions in the combustion, using also a shaker to do what is called the Kollner dome experiment. We did cold flow and hot flow experiments. This table is related to the hot flow experiment, which are more interesting for this presentation. So we test the behavior under ignition. We test the measurement or detection of a flashback, the transition of a flame from premixed to diffusive. We analyze the combustion instabilities, and also we analyze the signal in proximity of limb blowout. So the first test we did is the behavior of the system at ignition. At ignition, here we can observe the result of a measurement of optical probe. This is an accelerometer. This is a dynamic pressure sensor we had. So we can see that each time we give ignition pulse, both accelerometer and the pressure sensor react. And we see also that the optical system is immune from this disturbance. Another test we made, we changed the combustion condition in order to produce premixed to diffusion transition. In this case, both the piezo, which is in blue, and the optical sensor in red detect the transition. This plot on the top is the result of a chemiluminescence detector, which also, of course, detect the transition of a flame which changes color. This is the Kollner dome experiment. So with a shaker I showed before, we produce combustion instabilities, and both optical sensor and piezoelectric sensor showed a good agreement in both amplitude and phase response. This test was quite important also to analyze the phase measurement, because in some circumstances are very important. So we could show that optical data have enough good quality to make a measurement also of a phase, as piezoelectric sensor has. Here we come to the flashback. What is interesting in optical sensor is that here we are analyzing a very low frequency band, which is usually not used with piezoelectric sensor due to the noise. So here we are analyzing the 2 to 5 Hertz band with the optical sensor. They show the very, very, very good similarity. We have this double peak structure, which coincide with flashback events. As said, we cannot do this analysis with piezo. And so this proves that we can have a more reliable, physical, meaningful analysis of a flashback. And probably the low frequency band analysis may help also to identify flashback precursors, which are very important, as I mentioned, for the hydrogen combustion. Here we go again, analyzing the low frequency bands. These are scalograms in proximity of a limb blowout event. On top is the optical sensor, and the bottom is the piezoelectric sensor. The optical sensor clearly detects the moments in which the flame attaches and detaches from the flame holder, and this is not visible in the piezo, which is where the signal is essentially noise, and so we can easily very well detect the extinction of the flame in this case. So what happens is that it seems that optical sensing offers a reliable foundation for methodology to analyze low frequency data in order to detect the phenomena like flashback and lean blowout. And that is why we start analyzing these low frequencies, both with wavelet analysis and with fractal analysis. Result of this analysis and a little description of the algorithm is also presented in another document that we presented to the PHM conference this year. And I will give you the reference at the end of this presentation. So as I mentioned, we developed some wavelet indicators for limb blowout. We focus on limb blowout at that time. We are now ready to analyze also the signals in proximity of the flashback. So we have wavelet indicators that we developed, 2 different wavelet indicators, and here we show the value of these wavelet indicators. We called hard indicator and soft indicator in proximity of limb blowout, and we can see that the first one clearly detects the event, and the second one also gives some hints about the approaching of this event. If we do the same thing for piezoelectric, so the piezoelectric sensor indicators are on the bottom here, and the optical on the top, we can see that the piezoelectric, we cannot use the low frequency data to compute this indicator and provide a reliable determination of limb blowout phenomena. This is even more interesting. We did fractal analysis, so I spend a little bit more time into this plot. This plot shows in the dashed line the mass flow, and in the continuous line a fractal indicator as the Holder experiment indeed. So we know that when the mass flow here increases, we are approaching to the extinction of the flame and to the limb blowout. And we can see that as more we were increasing the airflow rate, more the Holder exponent was increasing. Another thing which is quite important is that this level 0.75 represents a quite reliable level that we saw in other experiments that I'm going to show you now. Okay, this is again, this is one, and again we have this increase from a normal combustion, say normal combustion, from 0.6 to 0.7. And these are other events. Again, we did the same experiments, increasing the air flow, and again we go from 0.6 to 0.7. So we have, it's quite a looks as quite a reliable method to prognose and track the evolution towards limb blowout. Of course, we repeated the same analysis for the piezoelectric, but as shown for the hard and soft wavelet indicator we described previously, again, we cannot use the low frequency data, which are crucial for the determination of the Holder exponent. So we can move now to the conclusions. So I want to recap here the sensing system. So it's made of two parts: a sensor with an interferometer in the combustor chamber and some electronics to analyze the results returning, the light returning from the interferometer, transform with the Piezo wedge, the spatial modulated spectral modulated light into spatial modulated light, and extract the pressure. So two parts, optics and electronics, and two interferometer, the Fabry-Perot and Piezo. Moreover, we use quite, in the end, it's not truly right, it's not truly white light. We saw that we have 50 nanometers light at full width, half maximum. And these are the concepts I would like you may remember. So we start with the need of reducing emission. So we need new method to produce energy, new method to control the combustion at this point. And optical sensors have very good characteristics. They can get a higher temperature, they are insensitive to MI, they have better signal-to-noise ratio. Meggitt has invested in this new technology, want to become a world-class integrator of these sensing technologies for aerospace and power generation. We presented our system solution for dynamic pressure measurement, which is based indeed on the combination of two interferometers and signal processing algorithm. Are secret and I didn't mention. And we presented also the result of the test we made to validate the optical sensing system in operational environment. And we made this ad hoc campaign, which allowed us to confirm that we have very good results, especially at low frequencies. And in the rest of case, the optical sensing system and the piezo sensing system are almost equivalent, but remind that we have a higher signal-to-noise ratio at low frequencies. And this provides a reliable foundation to monitor phenomena such as limb blowout and flashback, that are critical to transform the gas turbine into low or zero carbon emitting system. And this is where the hummingbird comes into play. I want also to give us some ideas of the current development. We made tests on turbines with optical dynamic pressure sensors since the first half of 2020. We expect to have an industrialization phase completed by end of this year and the entry into market in 2022. On the airspace side, we are also developing new high temperature static pressure, in this case, and temperature sensor. And we will have a second engine test in the first half of 2022. These are the reference I mentioned before, our two papers. You can ask to Sindhu or Vanessa. They will give you the PDFs. I believe that.
Thank you, Gianluca. We are now open for questions. Please unmute your microphones to ask your questions.
Hi, Sindhu. I received one on the direct messaging. Which features can be considered lean blowout precursors? Could you hear me, Gianluca? Sindhu, can you just confirm that you could hear me?
Yes, Vanessa, I could hear you well. Gianluca, did you get the question from Vanessa? Do you want me to repeat the question?
Hi, Gianluca. Can you hear us? I think we had a little challenge.
I don't know what should I say because I was waiting for questions.
It's the perks of doing live. Anyways, I had the first question coming. Which features can be considered lean blowout precursors? Can you hear me, Gianluca? Can you just confirm? I guess we are having a technical challenge. Let me try calling the COE.
Meanwhile, I would request the participants to drop your questions in the chat box.
We are very sorry, everyone. It appears that today we are having more technical challenges than usual. I'm on the phone with TCOE. We are trying to fix that so you can have your questions asked. In the meantime, if you have other questions, please send them on the chat. I already have myself 3 on the direct, and I see that Alfonso asked one on the chat. So we will come back shortly. So can you hear me, Igor? Okay, are you back? Gianluca, can you confirm that you can hear me?
Now, yes.
Oh, great. Sorry, everyone, about that. Let's get to the question. So first one was, which feature can be considered lean blowout precursors?
Well, in general, we found, so first I want to thank you for listening me without my video, etc., and for your patience and everything. Then comes back the answer. So the question is about which features are good for lean blowout. In general, we noticed that studying low frequency behavior of a pulsation, this gives pretty good result in terms of precursors. But indeed, low frequencies is just a symptom of something else happening. And according to some studies, like I cited in publications, like the study of Gotoda, for instance, there is a change in the fractal behavior of a signal that should be linked to the changing conditions in the combustion. I'm not an expert in combustion, I'm a physicist. Anyhow, what we did is that we extract, as I show in the presentation, some fractal features. Fractal features can only be computed using low frequencies, because basically we need to train a log-log plot in which on one side we have the frequencies and the other the fractal dimension. We need to push this log plot very low frequencies in order to have a good estimate. So coming back to the answer is for sure there is a change in the combustion behavior, which is reflected on the fractal behavior of a signal. So in the type of noise, for instance, which moves from pink to brown, and in general, so and this has an impact on the low frequencies. So in the end, studying the low frequencies is good, and if we want something more specifically linked to what happens really in the combustion, and I again cite this Gotoda paper, we should look to fractal features. This answers the question.
Thank you, Gianluca.
Yes, Vanessa. Gianluca, we have next question from Alfonso. Alfonso's question is, how does it compare in terms of price with the piezo sensors or other sensor alternatives?
Sorry, I'm not sure I've understand everything.
I'll read the question once again for you.
Yeah, it was a question from certain
Alfonso. Alfonso, yes.
And it's about sensors, but I didn't understand the question.
Yes. How does it compare in terms of price with the piezo sensors or other sensor alternatives?
Igor,
So
did you understand what she said?
Gianluca, it's the price in terms of pricing.
In terms of pricing.
Exactly, the Piezo sensors and the optimal sensors.
Okay, it's a question. Okay, so so far the effort of Meggitt is find a good industrialization strategy in order to reduce the price. what I can say is that at the stage we are, the prices are comparable, and we expect to be able to use cheaper components in the future, because we will better understand what is really needed by the market. So far the price is on the same level of a Piezo, but we have to remind that here we have new capabilities. So it's like to say, okay, a car is a car, and you can buy a Fiat or you can buy a Porsche. You can say, if you want to use to go to the office, maybe it's better to buy a Fiat. But if you want to drive more comfortably, this is not advertising. Fiat is, but you would need a Porsche. And in the case of low frequency analysis, probably we would need a Porsche. And so an higher price may be reasonable. Does it answer the question?
I think it does. It will be a premium product. Like you said, it will be a Porsche. So yes, it does answer the question.
Alfonso says thank you. So yes, thank you, Gianluca.
Thank you to you. It's already over, yeah, because we were late. But so I invite you to attend the session of the afternoon. Probably we will not have
as much challenges,
issues, and we have more time for the questions. Maybe
I have
so.
just one last one
me
from.
Straight away. Give you all the information.
Gianluca, if you agree, just to a last one from Luc Fromager. Would going to DC measurement improve the BO detection?
So the DC measurement, frankly, is not much useful for this, especially because what we want to do is to detect precursors, and the static pressure, indeed, we cannot see something really in the static pressure if we want to prognose the extinction of a flame. We should go more on the analysis of low frequency, but not up to the DC for the precursors of blowout. And also of a flashback, I imagine.
Thank you, Gianluca. Well, Luc, if you just allow me to last one. Luc Fromager also asked, the optical sensor can be put on a stinger right inside the combustor. Is this a benefit?
This is a benefit. I mean, in general, the optical sensor can get closer to the flame, and you do not need semi-infinite tubes. And as usual, when you are, not always, but usually when you can get closer, you have a better view of what is happening. Not always. Sometimes you have to stand a little bit back. But in this case, it's better to be a little bit closer. So in this case, optical sensor may bring a benefit, yes.
Thank you very much. Thank you very much for those answers. Thank you very much, everyone, for your patience today. It was technical challenges. It happens. We will try to fix it for next time. Thank you, Gianluca. If you all agree, we will move to the Mentimeter. So as usual, you have the code on the top of the page, and please rate it honestly. I know today was a challenge. So, but I hope the quality of the content was worth the technical challenges. Thank you very much, and please rate the session as usual. We will close this session in about 3 minutes at 11 a.m. sharp. Hope to see you on the next webinar, and I hope you enjoyed. Thank you very much.